These notes are going to cover the exponential equations part of the notes. So it's going to be graphing exponential equations as well as writing exponential equations. So to start off, we talk about exponential equations in functions back in Unit 2. As a reminder, the parent function is y equals 2 to the power of x. There isn't actually a parent function for exponential, but that's just kind of the one we use as a basis for everything else, or for as basics. So an exponential function is an equation where x is in the exponent. So the key word in exponential is that word exponent, because the exponent here is going to be a variable where we can actually change it. It's not going to be a fixed number like we're used to seeing. So the basic form of an exponential function is y equals a times b to the power of x. You may also see this as y equals a times b to the power of x with a dot instead of parentheses, which is also acceptable. I just prefer the parentheses because sometimes the dots can look like decimals. All right, now, as always, there are always meanings to variables that we use. So y and x are in every single equation we've seen so far, but the variables within or aside from that are typically different, right? So our a value here is going to stand for our initial or starting amount. So in a word problem, if it tells us we're starting off by investing $15,000 into a bank account, then that would be our starting amount. Or if we buy a car for $20,000, that would be our starting amount. And then what happens to that car or that bank account is going to be dependent on what our growth factor is or decay factor is. So your b value is going to tell us whether it's growing or decaying. So this can be a decay or growth factor. Now, again, that's going to be dependent on the value, right? So if the value is larger than 1, that is a growth. If the value is in between 0 and 1, then that is a decay. So anything in between 0 and 1 is a decay. Anything larger than 1 is a growth. All right, so let's look at some examples here, right? So we have a growth equation here, and we know that this is a growth because this b value is greater than 1. So we know for sure it's going to be a growth. Growth graphs typically increase as we go from left to right. So as we start off on the left side of this graph, it's going to kind of start flat, and then it's going to curve upwards to the right and increase. And it's going to go, I don't know, I don't really know how to describe the shape. It's like a curved shape that goes upwards. All right, now if we have a decay graph, a decay graph is if our b value is in between 0 and 1. So we know for sure that this is going to decay. And decay graphs are kind of the opposite. They kind of start off high on the left side, curve down, and flatten off towards the right. And it's not really flat, but it's kind of getting closer and closer to a boundary line. And that boundary line is going to bring us to our word asymptote. Now, the word asymptote is an imaginary horizontal line the function never crosses. All right, so what does that mean? So you'll notice how I've been talking about how the function's getting flat, right? So if I go into Desmos right now, we just graph, let's say, the parent function. So let's say I have y equals 2 to the power of x. You'll notice that the graph on this left-hand side is pretty flat, and it looks like it's on the x-axis. But if I were to zoom in, they actually don't ever intersect each other. They do not cross. That line is called the asymptote line, and in this case, it's our x-axis. But if I shift that asymptote up or down, then that asymptote is going to change. So for example, let's say I add a positive 3 to this equation. Well, you'll notice the graph is still getting flat, but it's getting flat at the positive 3 value. So if I look at the line here at y equals 3, right, you'll notice at y equals 3, the lines look like they're on top of each other, but again, they're not actually crossing. So that value at the end, that positive 3, is going to tell us where our asymptote number is. So if I change this, let's say I change this to, let's say I take my parent function, I shift it to -5, right? So now I'm down here. Well, now the line is, or the function is flattening out at -5, or the y value of -5. And you'll notice the asymptote here is going to be y equals -5 instead. So that last number is going to kind of tell us where its boundary line is. And I kind of describe this as it's like an electric fence. You can get as close as possible, as much as you want, but you don't want to get shocked. So it's always going to get closer and closer to it as you continue on to this left side. So if I keep going this way, it's going to get closer and closer to the line, but it's never going to intersect. So the goal is to get as close as possible without getting shocked, right? All right. So go ahead and draw an example of that here. So that, let's just say we have an increase graph. So let's say that's here, and maybe our asymptote is going to be right here. And I'm making a dash because remember that line isn't actually there, but we're going to use it as a representation. So that equation is always going to be y equals a number depending on where it's crossing, right? So if it's crossing at, or if it's getting flattened at +2, then our asymptote line is going to be at y equals 2. If it's flattening out at -7, then the asymptote equation will be y equals -7. Brings us into domain and range. Now, domain for all exponential functions, unless they're restricted, are going to always be all real numbers. And again, I'm pretty lazy, so I like to use the R symbol, the all real number symbol, which is an R with an extra line inside of it. And then the range, because the asymptote does exist, it does restrict our graph. So our range is going to be y is greater than the asymptote number itself. Now you'll notice I didn't put greater than or equal to. So it's not equal to because it's not going to actually hit the asymptote number. It's just going to get close to the asymptote number. So we don't want an equal to here. And the reason why it's a greater than is because the graph is above that asymptote line. There are situations where the asymptote will be above. So I might have an asymptote here and the graph might be below like this. That's a pretty rare case, but that can happen. In that case, that means that your graph is below the asymptote number. So you would use a less than symbol there. But in most cases, it should be above, especially on the problems we're about to do together. So on this first section, I'm going to be using Desmos to kind of transition us into using that as we prepare for later tests. So I am going to be using only Desmos for this set of notes. You can use a graphing calculator. It works the exact same, but we're going to use Desmos just for practice. So here we're given an equation, y equals 3 times 1/2 to the power of x. Now, we know for a fact that this is a decay. And the reason why we know this is a decay is because of this b value here. It is in between 0 and 1, and because of that, we know that that's going to be a decay graph. Just without even having to graph it. So I'm going to go ahead and go into Desmos and plot that. So I'm going to go ahead and get rid of that. Y equals 3, parentheses. To create a fraction, like 1/2, you're just going to use the divide button. So if I want to do 1/2, I'm going to click 1, divide 2. So we're going to use the division button there. Go ahead and close the parentheses. And then the exponent button. Can I get the assistive touch? Oh, it's not letting me. Okay, I'm trying to figure out how to show this to you, but it is the fourth key right here on the screen. It's the A to the B, so it's on the left side of this keyboard. So I'm kind of spamming it right now, if you can kind of see it on the screen. If you press that button, it'll bring it up to the exponent, and we're just going to type an x in. And we kind of see that this is a decay graph. It's starting on the left, and it's decreasing downwards to the right. And then I want to be able to plot this, so I want to create a table. To create a table, you're going to hit that gear icon at the very top here. Once you press that gear, you're going to press on the table feature, and you'll notice a table pops up. Now, Desmos isn't super great in comparison to graphing calculator for this because your table's not infinite, right? You're only given 5 values here. So you can increase it. So to increase it, you're going to click on the lowest x value. In this case, it's always going to be +2. That's how Desmos is. You can extend it by just pressing the enter button, so the blue enter button here. You can create more points if you want. We don't need to do that. I'm just letting you know that is a possibility. All right, so anyways, I want to graph this on my paper, and I'm going to have you guys graph 3 points. So we're going to graph what can fit. 2, -12 is not going to fit on my paper because I don't think I gave you guys enough tick marks for that. So we're going to go ahead and graph these 3 points, -1.6, 0.3, and 1.5. So I'm going to go to my table, and I'm going to record those values real quick. And then I'm going to plot them on my graph over here. Okay, once I've plotted my 3 points, I'm going to go ahead and try to connect them. Before I do that, I do want to talk about what is our asymptote here and what do we need to stay away from. So again, the asymptote earlier is that imaginary line, right? And that's usually the number being added or subtracted to our entire equation. Well, in this case, there is no number back here, right? There's no number written back here. So it's kind of like adding nothing. Adding 0. So our asymptote equation is going to be y equals 0. And I can actually check that when I go to Desmos. If I go to box 4 here, box 3, I can type in y equals 0, and I'll see that my asymptote is against my function. I want it to be right up against it. If it's too far away, it's not considered an asymptote. So for example, if I do like -1, that's too far away. They're not even close to each other. And if I do +1, that's going through it. So we don't want that to happen. So 0 is going to be that perfect number there. And that means that I technically have an imaginary line right here, and you don't have to draw those tick marks, but I like to draw them as a guide. I don't want to pass that point. So when I connect my points together to make this curve, I want to make sure I don't pass that asymptote line there. All right, the next thing we're going to do is answer these questions. So the first question is, what is our x-intercept? Well, our asymptote line is on the x-axis, and that means that our function has never gone across the asymptote or the x-axis, which means we don't have any x-intercepts here. Y-intercepts, we have one y-intercept that's going to be at the point 0, 3. Your domain here is going to be all real numbers, and the range here is restricted by the asymptote. So your graph is above the asymptote, right? Everything is above this green line, so it's going to be a greater than symbol. Y is greater than 0. And your asymptote number and your range are always going to be related because that's how it's restricted. Moving on to the second equation here, we have y equals 2 to the power of x minus 4. And you're probably wondering why there are no parentheses in this equation. So it kind of is this, but we don't write the 1. So we talked about this in the past, right? Multiplying by 1 doesn't affect our problem, so we kind of normally never put it there. So if I have x on my paper, I know that that's technically 1x. I'm just not writing the 1. So here, our b value is 2. And that is greater than 1. And for that reason, I know this is a growth. Now, because there is no 1, we don't really need that 1 in the front. That's why there's no parentheses around that 2, because it's just kind of unnecessary. All right, so I'm going to do the same thing. I'm going to plot this into Desmos, and we're going to get a table, or we're going to get a table from that so we can get some values. So y equals 2 to the power of x minus 4. And again, you can use your graphing calculator on this if you want. I'm just choosing not to have one because, you know, we need to learn how to use Desmos. So I'm going to create a table from this. So hit the gear, press the table, and I only need to plot 3 points. So I'm going to plot the points that I feel like are the easiest here. So maybe we'll do these 3. -1, -3.5, 0, -3, and 1, -2. Now, you don't have to pick these points. You can pick a different point if you want. These are just the 3 points that I'm choosing. And the reason why we're doing 3 points is it kind of gives us a good image of what this curve looks like. So -1, -3.5, 0, -3, and 1, -2. All right, so let's talk about where this asymptote is so that we know where to restrict this graph. So I see the back number here is -4, which means my asymptote is going to be restricted there. So y equals -4 is going to be that line. So I'm going to find y equals -4 on this graph. So it's going to be about right here, right? So that's my asymptote line. And I don't want my function to pass that. So I'm going to go ahead and draw a curve that kind of flattens out at -4, but it doesn't cross -4. Next, I'm going to answer, do we have any x-intercepts? In this case, we're going to have x-intercepts just because that line is going, or that function is going to continue forever. So to find the x-intercept, right, you can either look at your table or you can just tap on your graph where it crosses the x-axis, and that's going to be at the point 2, 0. All right, we do have a y-intercept as well. The y-intercept here is 0, -3. I can see that on the graph right here. Domain here is going to be all real numbers because it extends infinitely to the left and to the right. Your range is restricted here by the asymptote. So your range is going to be y is greater than the asymptote number, which is -4. The entire graph is above -4. Moving on to the next example, go ahead and type that into, actually before I type it in, I notice that this is going to be a growth because my b value is greater than 1. So I'm going to go ahead and put growth here. Y equals 4 times 2 to the power of x minus 1. Oh, sorry, plus 1. I just realized I typed that in wrong. Okay, there we go. All right, and then I'm going to go ahead and get a table from that. So gear table. And then I'm going to go ahead and plot points here. So I'm going to just plot these 3. So -2, 2, -1, 3, 0, 5. All right, so I have -2, 2, -1, 3, 0, 5. All right, let's find our asymptote here. So our asymptote here is going to be restricted by +1. So y equals +1 is my asymptote equation. So it's going to be right here on the y-axis. So here's my imaginary boundary line. Go ahead and connect my graph here. So first question is any x-intercept. So again, the asymptote is above the x-axis here, and it's never going to touch the asymptote, so it's definitely not going to touch the x-axis. So we don't have any here. And we can kind of see that on our graph as well, right? So like if we look here, we know that this thing's never going to touch the x-axis. It's literally above it the entire time, so not happening. Y-intercepts we do. We have 0, 5, Domain is going to be all real numbers, and then your range is going to be above +1. All right, we're going to move into the next section, which is writing exponential equations. And so when we're writing, it's actually fairly simple. The most complicated part is probably deciding which formula to use. And we have two sets of formula we're going to use here. Both of these can be used for growth or decay. So this left one can be growth or decay, because we kind of saw that in the previous. Now again, if you don't like this dot like me, you can use parentheses here. It means the same thing. On the right side, these also can be growth or decay, but it's just dependent on the symbol we have inside. So if you notice, we have a positive and here we have a negative. When we are adding an R, that's going to be a growth. And when we are subtracting R, we have a decay. So then now the question comes, well, how am I supposed to know which growth or decay formula to use? And that's going to be based off a different thing, and we're going to talk about that in a second, but let's go ahead and talk about some of the other basics. So as the front page said, A is going to be your starting or initial amount. And same thing right here, so I'll go ahead and put that down. Okay. So, and then on the front page, we talked about how B was the growth factor, growth or decay factor, just depending on what's happening there. So this can be growth or decay factor. But typically, when they give you that, it's going to be given in a rate form. So it's going to say rate. If I can change the color. And when the rate is given to you, it's given to you as a word, not as a percentage. So examples of that could be halved, doubled, tripled, etc., right? So I can move on and on and on. So you can say doubling, you can say triples, any of that stuff is fine. Actually, I'll put triples just so we have some differences there. All right, now over here we have the variable R. Now R also means rate, but this rate is a percentage. So you'll know which formula to use based on how the rate is given to you. If the rate is given to you in word form, if it says doubling, if it says it's getting halved, that's when you use the left side. But if it gives you a strict percentage, saying it's growing by 5% or decreasing by 3%, then you're going to use the right side. And the tricky part about this is you do have to turn that rate into a decimal. So we're going to practice that really quick just so we remember how to do that. So we're going to do some examples here. So let's say I have 15%. If I have 15%, I want to turn that to a decimal. There are two ways. You can either move the decimal place to the left 2, or you can just divide by 100 in the calculator. So 15%, the decimal would be here, so I'd move it over to the left 2, and that would be 0.15. If I have, let's say, 7%, well, 7%, the decimal is here, and if I move it over 2, the decimal will be here now, and so you want to add that extra 0. So this is going to be 0.07 as a decimal. And then the last one, as an example, we'll do 3.4%. That's going to be, whoops. It's still moving 2 over, right? So it's going to be 0.034. You're still going to keep that 4, but in this case, the decimal is already there, so you're going to move from where it's at. All right, so those are going to be your 3 examples for that. Now, T is representative of time. What color should I use? What have I not used? Pink. Now, sometimes we call this X. So if the T makes you uncomfortable, you can actually replace that T with an X. Same thing, doesn't matter. All right, so now we're going to practice this with the next 3 problems. Now, in these next 3 problems, you have to decide which formula to use, and then you can actually create the equation and then solve the problem. So on the right side here, on the left side here, remember, we're only going to use this formula if the rate is given to us as a word. And we're going to use use the right side if it's given to us as a percentage. I need to stop getting my left and right mixed up. All right, so we're going to start off with number 1. You purchase a car for $30,000 and it depreciates in value 2% every year. How much will it be worth in 10 years? So off the bat, I notice I need to figure out what formula to use. And that's going to be based on how the rate's given to us. Do we see the rate as a percent or a word here? Now, I see here that the rate is given to me in a percent form. And because it is a percent form, I know for a fact I'm going to be using the right side over here. The question now becomes, which formula am I going to use? Am I going to use a positive or the minus one? So am I going to be growing or decaying? Now I notice a word here says depreciates. And depreciates means going down, right? It's going down in value, which means I'm going to be using this formula with the minus sign. So I'm going to go ahead and copy that down. Y equals a, 1 minus r to the power of t or the power of x, whatever you prefer. It does not really matter. I'm going to use x just so I can show you that it really doesn't matter. And then what you want to do is you want to create your equation. Now, typically when we're creating equations, we want to leave y and x alone because our independent and dependent variables could change. So we're just going to try to find a and r here. A is going to be your starting amount, and your r is going to be your rate. So let's see here. Our starting amount was 30,000, and your r, your rate here, is 2%. And we want to turn that percentage into a decimal, so it's going to be 0.02. And I'm going to go ahead and write my equation here. So it's going to be 1 equals 30,000. That's my a value. My zeros look crazy. Parentheses 1 minus 0.02 to the power of t or the power of x. Again, either way is fine. Now you want to make this in simplest form, and typically on your STAR exam, it's also going to be similar. It's going to be in simplest form. So I'm going to go ahead and simplify this parentheses set. So that's going to be y equals 30,000. And that's going to be 0.98 to the power of x. Oopsies. So that's our equation that we have here. All right, now once we go ahead and we have our equation, we're going to answer the question. Because again, there is a question in this problem that we haven't answered yet. How much will it be worth in 10 years? Now, if we're looking at the number of years, years in this case would be time, t. Now, obviously, we replace the t with an x, so we're going to plug that in for x. We're going to plug in 10 for our x value. So you have 30,000 times 0.98 to the power of 10. So let's go figure out how much this car's going to be worth in 10 years. So I'm going to get rid of this graph. We don't need that anymore. 30,000. We don't want to use commas here as well because commas can give errors. We got 0.98 to the power of 10. And you'll notice I have this value down here. Now, remember, we are talking about the value of a car, which is money, and we only want to keep 2 decimal places if we're talking about money. So it's going to be 24512.18. And this is going to be money, right? So 24,512.18 is going to be our expected value after 10 years. All right. Moving on to the next question, we have bacteria doubles every hour. If we start with 3 bacteria, how much bacteria will there be after 1 day? So just based off of this problem alone and just reading everything I have, I don't see a percentage in this problem. And because there is not a percentage, we're going to be using this formula over here on the right. On the left. Oh, okay, so that formula is going to be y equals a times b to the power of x. You can use that multiplication dot if you want. Again, I'm using parentheses. And we want to leave y and x alone when we're creating our equations. We're just going to fill in that a and the b value here. So leave everything else, leave y and x alone, fill everything else in. So our a values are starting amount. Well, here it says we are starting with 3 bacteria. So a is going to be 3. And then our rate here is going to be our B. Remember, that could be a grow or decay. Well, what's happening to the bacteria? It says it doubles every hour. Doubles as a number is 2. So our equation is going to be y equals 3 times 2, our rate, our B value, to the power of x. So that is going to be our equation. And now we're going to solve the problem. The question says, how much bacteria will there be after 1 day? Now, the most common mistake here is people plug in a 1 for x for their time. But the issue is the bacteria is doubling every hour. So every hour it is doubling, not every day. So we have to consider this in hours. So if we see that it wants us to calculate for 1 day, yes, that means we have to plug in for x. But more importantly, we need to calculate that in hours. So 1 day is 24 hours. So we're not going to be plugging in 1 for x, we're going to be plugging in 24 for x. So it's going to be 3 times 2 to the power of 24. And that should be a giant number. 3 parentheses 2 to the power of 24. And we are given this gigantic number, and that's how much bacteria there will be after 1 day, obviously given the fact that nothing has decayed yet, right? So all your bacteria survive. So 50331648 bacteria. All right, moving on to the last problem here. Did I write that down right? 331648, yeah. All right, moving on to the last question here. The population of a town is currently 38,300. The town grows at an annual rate of 1.2%. Why do I have 2 periods there? That's so strange. Anyways, oh, it's not a period. It's a percent symbol and then a period. What will the town population be in 7 years? So first thing I see is the percentage here. If I see a percentage, I know that I'm going to be using one of those right formulas. And I notice that it says growth. So I'm going to be using the plus one. So y equals a 1 plus r to the power of x or t. All right, and then we're going to leave y and x alone. We're going to plug in everything else. So we need to find a, and we need to find r. A is your starting amount. The starting amount here is 38,300, there we go. And then the rate is 1.2%. We want to turn that percentage into a decimal, so it's going to be 0.012. So we're going to plug that information in. So I have y equals our a value of 38,300. 1 plus, this is a growth problem, right? So 0.012, close parentheses, to the power of x. Now we are going to simplify this parentheses set. We always want to simplify, especially on a STAR exam as well. 1.012 will be the simplification of that. Go ahead and bring everything else down. I know I kind of did that in a weird order, but it's survivable. It's okay. Okay. Now, the question is now, what will the town population be in 7 years? Now, 7 years is time. We're going to plug that in for x. So we have 38,300, whoopsies, times 1.012 to the power of 7. 38300, parentheses, 1.012, 1.012 to the power of 7 years. So that's going to be 41,635. We are talking about population of a town, which is either people or whatever it may be. Because it is population, we want to round to the nearest whole number. So it's going to be 41,635. All right. And that would be about the amount of people, right? This is just an estimation. Based on this trend, there should be about that many people after 7 years.